This class is about sulfur. Sulfur plays an important role in pigments examination, and in particular will be the protagonist of ultramarine. Ultramarine, natural and artificial, they both contain sulfur. There it is, sulfur 16 over here. Sulfur has a K-alpha line at 2.3 and the K-beta line is 2.4. As usual, when it comes to these low energies, X lines, we want to be sure that we have a good percentage of the X-rays produced by the target that can reach the detector. We are going to use our online calculator. We input air because we want to go through a thickness of 10 millimeters, so we use this value as a reference, and we input the X-ray energy 2.3, that is the K-alpha of sulfur. The calculator gives us this value, transmission 65%. More than half of the X-rays can reach the detector. We have hope that we can see sulfur even when we have low concentration of this element. And so now we go in the lab to start testing a material that has a lot of sulfur. For the analysis of sulfur, we are going to use my little bit collection of minerals. So we have sulfur, this mineral over here. This one is actually found in Sicily, and we start to analyze this material. So we put this one under the spectrometer to check what we get. This is the spectrum of the sulfur mineral, so just sulfur. We have a very strong peak at 2.3, and the counts you see up here basically is in the order of 190,000 counts. So we have plenty of X-rays. Compare this number with that of, for example, aluminum that we saw in the previous lesson. So this is a very huge number, so we can detect sulfur very easily with this with the technique. And now, okay, once we saw that in this region we see sulfur very clearly, we can move to something else where there is less concentration than in the sulfur mineral. The other material where we find sulfur just with less concentration is vermilion, the pigment over here. We have both the artificial and the natural mineral, cinnabar. We try with the vermilion artificial over here. Vermilion, this is important pigment, red pigment, is a mercury sulfide. So there is one atom of mercury and one atom of sulfur. Let's check it. So this is the spectrum of vermilion compared to the one of the pure sulfur. We see that we have the peak of sulfur over here, and also you see the shape of this peak is quite strange. It looks like the overlapping of two peaks. And indeed, this is a case. There are few in XRF spectroscopy, particularly for pigments, where we have lines overlapping. So this one basically will be the line, M line of mercury, from the mercury in vermilion. And this other one at 2.3, this other peak, is the one actually from the sulfur. Generally, vermilion is identified enough by its mercury content, but definitely with XRF spectroscopy we can also check the sulfur content. Let's move to something else. Another important material that we can check is gypsum over here in the pigment check. Gypsum is not really used as a pigment, but is present as a ground preparation for paintings. Gypsum is a calcium sulfate, so there is a calcium, there is one atom of sulfur, and then there is oxygen and water, hydrogen and oxygen again. So basically, again, we are with one atom calcium and one atom sulfur, and these two are the ones that play a role in XRF spectroscopy. Hydrogen and oxygen, it's like they are invisible to the XRF. We expect from the measurement of gypsum basically to have the same intensity of vermilion. Let's check it out. So there it is, this is the spectrum of gypsum, the blue one. So in gypsum, you see, we just see the peak of sulfur, and the peak has the usual shape because there are no other peak overlapping, like in the case of vermilion. We see from the formula of gypsum that is a calcium sulfate hydrated, that of course we have sulfur over here, calcium, and the other elements do not play a role in XRF spectroscopy because they are low atomic number element, hydrogen and oxygen. In the case of gypsum, we have a peak that is comparable to that of vermilion, because basically we just from the point of view of XRF spectroscopy, the molecule is made just of calcium and sulfur. The other elements don't play a role. Okay, let's see something else where we have definitely less sulfur. Now let's check a pigment where we have less concentration of sulfur. Ultramarine artificial, which is the same of ultramarine natural, the same formula. Here we have a silicate lattice where there is also aluminum that play a role and other elements that actually are not important. There is a sodium, there is silicon that actually play a role, and then oxygen in it. We expect to be able to see sulfur, but less of it. Let's double check. Let's see the spectrum of ultramarine artificial. Again, this is the formula, so we see that we have sodium, aluminum, silicon, and then we have 3 atoms of sulfur over there. So basically it's a silicate lattice where there is also sodium, aluminum and sulfur. Or basically the atoms of oxygen don't play a role in XRF spectroscopy because too light, and consequently the spectrum that we get is the green one over here, so we still see sulfur. There is enough. Less than the other case, less than, for example, we saw in vermilion, less than we saw in gypsum, but definitely the peak of sulfur in ultramarine is detectable, and in any case has a good count number. So you see here, I mean, it's small compared with the pure sulfur, but the number of counts is in the order of 20,000. So it's still a big number, so it's definitely something that we can detect.